profile. And to make your life easier, so we have all data labels. So we see that it's a binary with 1, with high probability with allergy, and with 0 means may not be necessary to have allergy. But it doesn't mean that the label is correct or not. Just assume this is a ground truth. And your task is to find a model or find a way saying that if I give you more data without giving you the labels, whether you can predict whether it's 0 or 1. So the problem is, what kind of steps are you going to tackle this problem? So for example, these are the data given to you, and this is the task we're asking you. So I'll ask you to predict the labels of these 3 data traces, and these are given. How can you do that?
You can try linear regression.
Linear regression. Yeah. Can you briefly describe the idea of linear regression and how you're going to do that? How you define this problem under the concept of linear regression?
I would assume this is this is multi-dimensional data, and you can fit a line sort of on it, or maybe a multi-dimensional line as well.
Yeah. So it can. So I try to summarize. So all of the data can be visualized with certain distribution, and we want to find a hypothesis to briefly represent this distribution. So no matter what kind of new data you have, so you can fit in the distribution and find the corresponding label that help you to predict. But of course, this linear regression is one of the way. You have a lot of machine learning algorithms to deal with that.
This would be classification, right?
Sorry?
This would be classification.
Yeah, it's a classification, yes. But typically, this linear regression and linear logistic. So later, you're gonna find that there's a little trick to switch between the continual value, real value prediction, and the discrete value description. So it's a regression and classification. So now we start with this kind of supervised learning, and let's take a look how this problem can be formulated. Of course, one of the ways to start with is probably 5 data traces is not enough for you to learn from that, because with a high probability that the output of your learned model is still kind of random. So here you can also do that is you can keep collecting a lot of new data samples, and of course you have to determine what kind of data you are going to collect. You necessarily don't want to have a very small scale of value. In that case, you don't have enough capacity to learn a lot. Of course, you don't want to collect all of the data, like billions and a lot of gigabytes of data that make your model slow to learn, because it takes a very long time to find those hidden patterns within a large-scale data set. So there's a trade-off. And the second one is typically a lot of machine learning tasks can be formulated as an optimization problem. Well, we can, in general, an optimization problem can be written as a minimization of certain function. Of course, here, you can also say that something we're going to minimize is something cost or penalty that we want to avoid. You also can use maximization of certain, like the maximization of revenue, or maximization of reward, but sometimes maximization and minimization can be switched in different ways. And in this kind of formulated optimization problem, so W, as I noted, is the one we want to learn. So what is W? Here is kind of represent the model itself. For example, if we're working on linear regression, so y equals ax plus b, so here the a and b are something we're going to learn. Or also, for example, if we're training a neural network, for example, convolutional neural network, residential neural network, what we're doing is the weight on the neurons in different layers are so W consists of a matrix of all of the value of these neurons. So typically it can be a vector, can be a scalar, can be a vector, can be a matrix, can be a lot of different kind of data structure. And of course, the these feasible model parameters could be restricted within certain range. For example, you can limit it between -1 to +1, or you don't have any limitation on that one, so you just run the algorithm to find whatever things give you the minimizer. And of course, it doesn't mean minimizing optimization formulation is the most common way that we can formulate the task. But it doesn't mean that all kinds of machine learning tasks is solved by optimization problem. For example, there are some tasks or algorithm depends on counting or discrete one or statistics. For example, the k nearest neighbor. So typically, optimization may not be the top one way that we're trying to tackle. Of course, there are other exceptions, so I will leave this for you to explore a bit. And then so now here we want to formulate the problem in this form. So we have to define how we can represent this loss function. So any idea on what should be put in this objective function?
Training data?
Training data. So how you denote this objective function. So training data should be fed into this objective function to give you certain output. Yeah?
To optimize the parameters.
Yeah, we're going to optimize the parameters. And how you can define this f?
Based on your case.
Start with experience and
So, like you mean finding the subtraction or kind of the difference between the prediction and the actual value, the ground truth?
Yeah. How about you?
Based on your case, if you want to enhance something, then you can put it as an objective function.
For example, in the supervised learning task, as we showed before, then how you can define this objective function?
Or supervised.
use experience.
Experience, yeah. A very good idea is, as you said, so we're trying to learn something. So what we are going to learn, we're trying to predict the data labels as close as its ground truth label. So there are different ways to narrow this one. For example, you have training set. The first page I show you, you have the ground truth label. Definitely you can quantify, you can say that I want to set is a difference between my predicted label and the ground truth label of the training data. You also have another choice because you want to minimize this one because you are going to predict the labels of test set. You can also define the cost function based on the test set. And also you can also define this cost function on the test arrow. There are different definitions. You define the difference between these three. If you are the one that should that solve the problem, which one you're going to choose? The loss function based on the training data, or the loss function based on the test data, or the loss function based on the test set? Training data, why?
Because you train the model on the training data and then you can test it. To optimize the model, you have to run the loss function on the training data.
So it sounds great because at least you have when you calculate the difference, at least you have one of the thing you can compare because the ground truth of training data is provided. So is there any problem when you are trying to minimize the training data error? The training error. Is there any problem?
There can be overfitting eventually.
Yeah, because so if overfitting, how you define overfitting?
Like the training error is too low, but there is still test error which is higher than the training error.
Yeah, so in other words, somehow you learn too specific to your training data. So if your model is used to train on the test set on the data you didn't see during your training process, you're gonna fail. So there is a high probability that you cannot predict the test data label correctly. But later we'll say that, but as you may feel that a lot of people are still using training data, and why? So ultimately, we're going to say that we're going to minimize the test error because we don't really care about training error, to be honest. But in reality, we use it. There are a few reasons. But before doing that, we were trying to say that our ultimate goal is to predict the data labels we didn't see. So ideally, we want to minimize the test error, which is the expectation over, so here the expectation is taken over the randomness of test data. And the one in the bracket is a loss function with your learned model W, and the subject I will be the index of test data. Because there are a lot of, you will never know how many test data you are going to work on, right? You can be given a task set, but in reality, for example, when you interact with ChatGPT, ChatGPT doesn't know what kind of sentence you are going to input. So it should be, the model you learn should be able to deal with the data that not covered in a data set, that is a test set, for example. In here, as I said, typically we're tackling a very easy case. We assume that task distribution is identical and independently distributed. Here is how expectation is taken over, and here Fi could be the cost function you decide. For example, as we mentioned, we are trying to minimize the cost function defined as the difference between your predictor label and the ground truth label. But there are numerous ways to define this difference. You can have a direct subtract between these two terms. You can also have an absolute outside of this subtraction. You can also take the square of this one. So there are a lot of functions that you can take outside of this to denote this kind of difference. So let's return to this easy example about supervised learning. Here is the test error. In a more sensibly, let's start from a very easy one. It's the absolute error between the label you predicted and the label of the test data set. And here, well, of course, this can be substituted to whatever formula that can represent the difference between two values. And the expectation is taken over the test examples. And in this case, because of this randomness, ideally we want to handle non-limited number of data. So here we can imagine we are taking expectation over infinite data, and we can also, but somehow the problem is we don't know the y-hat, right? The subject J is the index of test data. We don't know, and we don't know how many of test data we have. We don't know the label of it. So we are in a big hope that the data we're training have similar pattern as the data we're going to use in practice. So that's why we need to train. If the training data have no relationship with the test data, so it means the model you're learning have no idea on the pattern of the data you didn't see. So here we have a very strong assumption is that the training data we're using, or the training data set table I showed before, should have similar distribution as the test data. But know that the test data may not be the same as the data table I showed in the second one, because the test here, the test is a very general definition on all data you didn't see. But of course should be of your research interest, of the problem target. Otherwise, you see, the training cannot help you to have a good test error. So because of the nature of this test data, which does not have labels, so we can never calculate this error. Because we don't know, we don't have the exact distribution of the test data. So we're using different ways to approximate. As just before, so there are another two ways. Is the first one is we're trying to use the test set error to approximate, because the test set is provided. And then we're seeing that in total we have m number of examples which is available for you to validate the performance of your model. And then this error is defined as the average of the differences between your predicted label and the ground truth of the test label. And of course, so here the difference is if you compare this equation with the form problem with the previous one is here's the expectation, and this one is just an average or mean over a finite number of data, which is included in your data set, in the test data set. And there's a golden rule that we typically follow in machine learning is that you cannot include your test set during your training process. Otherwise, you're cheating, right? Test set should be something that you use after finishing all the training process. So here, the number one rule is the test set can never influence the training process. Those data cannot be included. Otherwise, we cannot say it's a test set. We can call it like a validation set or some data without proper label. Then otherwise, and of course, we have the risk of overfitting the test set. And as you have learned in your previous courses, there will be a lot of ways to tackle the problem of overfitting. So here, we're back to the test arrow. So the test set arrow may not work. Then we have to step back again to say that what are other arrow functions that can efficiently approximate this test arrow. Another one is training arrow. So in the training set, we may have n number of data samples, and here this design, we can just replace the previous m with n. So here the n is the training data samples. And the loss function is defined as the average of overall training sample arrow. So here are the typical way we're going to solve it. Just quickly go through it. The first step is you should have enough data for you to train. Yes, have a question?
Is the tester the error that we find on the test data set, like on the samples itself, maybe due to sense error or something like that?
Oh, sorry, pardon me?
I'm sort of having trouble understanding what the test error is. Is that the error that's there due to some sort of sensor miscalibration or something like that, or?
The test error.
Yeah.
So the test error is, so let me try to illustrate another way. In this data, in the test data set, you can assume that this one is randomly aggregated from all of the test data. This is finite, right? So without all of this test data set, so for example, this is a test data, but only part of them available data set. So for a finite number of data, how you calculate the expectation mean? Yeah, right? You take average over all available stuff. But here when m goes to infinity, so another way is to denote that expectation. And here this expectation is taken over all data, test data samples. It should be within, for example, 1, 2, 3, and infinity. So the only difference is one is average over a finite number of data set, test data, and the other one is expectation. But that is a definition of
data set.
It's typically there are different ways to define your test data set. If you are only asked to predict the labels of a given data set, so you can use this to approximate the test error. But in most of the cases, like reinforcement learning, unsupervised learning, or interaction with generative AI, you have no idea. You can use this M is the historic data, the one that you can search on the internet. They are the past. But here is include something that probably happen in the future. So it's just a definition difference between average and expectation. So a typical way to solve a supervised learning is, first of all, we need to have enough number of data. And the second one is typically we want to separate the data with training set and validation set because we don't know the test data, but somehow we want to say that whether the model we learn are too specific or too general, how we can have a trade-off. So that's why we will have a validation set. But typically, you also have the choice without validation set. You can train the model with all of your training data set. There's no problem, but it's a trade-off based on your own design. Then another way is after you learn the model, there are a lot of hyperparameters when you train the model. Then another way is how you can tune the hyperparameters to give you a better performance on the test set, or a validation set, sorry, it should not be test set. And then we are the one that give you the best performance, the hyperparameter give you the best performance when we choose as the final model parameters for the test, for the trained data set. And then you're using this RepLab model and run on the test data, which give you the final results. And definitely, this can cause overfit because you assume that the validation set is something you didn't know during the training and it's already included in your training data set. But there are a lot of problems. A great question that you just asked about the difference between test error or test data error, and of course the training data is, so here for the test one we use M, or for training data we use N. You can see that different number of N will give you different kind of performance. So of course there are a lot of follow-up questions on how many training data you have to use during the training, how many training data you're going to use per each epoch, in each iteration to update. So those are all kinds of hyperparameters you can further tune. And today we're going to cover the very first algorithm to solve it, which is called gradient descent. And of course there are a lot of variants to help either speed up the convergence of gradient descent, or even improve the performance of gradient descent, or even there are some problem with the gradient descent, and there are some additional techniques to help address this problem. And later, in the next half of this lecture, or early next lecture, we'll also cover famous variant stochastic gradient descent. So whoever interacts with neural network, you're gonna know that stochastic gradient descent is used much widely than gradient descent, and later we will talk about why. So before doing that, I believe a lot of you have used different kind of programming languages, but probably you're working with PyTorch, PyTorch, and Jupyter, or those frameworks that frequently used for training. And all of these supports gradient descent. So this is the indicator to say that why gradient descent is still a main way to help you train your models, because it can cover as many questions, cover many general cases. This is not limited to, of course, I think gradient descent is not limited to machine learning tasks. Actually, it's a basic algorithm for optimization problems. Then, how many of you have interacted with any of these machine learning framework? Have you ever played with gradient descent? How do you feel? So basically, the algorithm itself is hidden behind the lines that you type in, right? Whenever you want to use stochastic gradient descent, you just define the stochastic gradient descent in your model. For example, the step size you're going to update in your gradient descent, and you just optimize during the training iteration. So you don't have to type in the details about gradient descent yourself if you are directly using this one. And of course, you can also start from scratch, where you do not necessarily to directly call the gradient descent function in this programming framework, but rather that you can type from there. You can say that you calculate the gradient and then use the gradient to update the model. And then the problem is how this is implemented from scratch. Anyone has a very high level summary about how gradient descent works? So at least we can see from the name, so gradient descent. So we have to calculate something called gradient. And then we're hoping this gradient can give us a lower number of this test error, the cost function, right? So here, let's get back to the very first or easy one to deal with that. So previously we showed that a cost function or the training error can be defined as the absolute value of the difference between the predicate label and the ground truth label. Another way is you can use the least square function. So here, let's assume that we start from this least square problems. Our optimization is to minimize over all in the real value area, and our target is to learn the model parameters W. And the cost function is defined as the difference between the predicate label is W transpose X. So here W again is the model parameters, and this X is the data, the training data samples available to you, and index I is the index of training data. And the second one will be the ground truth label of your training data. So here we call the one in the red as objective function or cost function or error function, training error function specifically. And sometimes we'll also say this is a loss or training loss. But of course, in details, the loss and objective function may have different definitions. And also, it's also different from the training accuracy. But roughly say they are correlated with each other. The second one is for any optimization problem, we are subject to certain kind of constraint. So normally, for example, a neural network, we don't necessarily specify a very limitation of that one. But for example, in linear regression, it can help you to, if you know the region of the optimal solution, you can actually add any constraint you want. For example, let me think about any. Do you have any examples like what kind of constraint you can consider when you're trying to learn a machine learning model?
House price is estimate.
How the price is estimated?
Yeah, like the square, how many rooms.
So for in certain cases that the one that you learn should be strictly positive, for example, then you have to apply this constraint to it. But typically for learning models, so that is a requirement for the input for the training data. So typically there is not any limitation on the coefficient, which is the learning model we're learning. And then once we can define the domain, we're trying to learn this optimizer. So in the minimization, it's called minimizer. And this is the one, ideally we want to find the one that gives us the minimum value. But of course there are different ways to do that. It depends on the domain of these parameters. Of course, the first one is they're based on whether this W should be continuous or discrete. We have a continuous optimization. For example, we in least squares and support vector machine. And in another cases, we can also formulate these optimization problems as a discrete optimization. For example, in decision trees, where there are certain rules that you have to follow. And also there is a mix of this continuous and discrete value. For example, in k-mean, in that case, the distance is something that are continuous, but the number of clusters is something discrete. Then we never given the least square, you can plot this the function of the training accuracy. But in general, we don't know what is the relationship between the label and the training data. So in general, we can draw this plot. Here, our target is to find the one that gives us a minimum in the valley. So we call this kind of point as a critical point. But of course, due to this non-convex nature of the data in reality, we can have a lot of local critical point. Some of them could be local maximum, so they are the top of different area, and then we will have among all of this, there will be one or some of the local optimum give you maximum, give you the global maximum. And of course, if you have top, then you have the bottom. So there are a few local minimum, and the one that gives you the minimum over all local minimum is the global minimum. And there are different area that have no idea about the optimum and minimum, we call it like inflection point, where in the case that the direction of the curve change, or in the region of the critical point. So it's total like a in a horizon. So everyone have this exactly the same value as others, no matter what kind of parameters you are changing. But among this one, we're going to find the point, the minimum. And there are different ways to find that. So typically we observe that the one who gives us a minimum have a horizontal tangent line, right? So here we typically to say that the derivative at this point equals 0 will give you something that is stable. So when the data when x get closer to this one, so nothing can be lower than the data around this point. But the problem is we can find this so-called stationary point by making derivative equal 0. But in most of the cases that the stationary point that give you the 0 derivative doesn't mean it's a global minimum. Unfortunately, for some sets of this machine learning problem, the local minimum implies the global minimum. For example, when we are working on these least squares, we will get back to this question. We can take the derivative and make it 0. So here is, you take the derivative, make it 0, so you put something on your left-hand side to the right-hand side. And so of course, there will be one of the assignment questions related to that, how you can calculate the derivative of least squares. Then, what kind of computation effort you have to pay if you make these derivative as 0? So how many number of lines you have calculated? Like, what is the computation complexity of solving the problem by making derivative as 0?
The number of training examples? No?
Just for this case, no, we're not talking about training process. Right now, I think the one that I forgot to mention is you don't have enough number of conditions to do that. So for x-axis, the training data set is x1, x2, and xn, for example. So this is your training set. And for each of these one will be a vector. So x1 will be like with d dimension. So you have n number of data entries. So this is what x looks like. W is the one you're going to learn. You can see it's in the dimension of d. So W is in dimension of d. And of course, y is also in the dimension of d. So y is the labels of our training data set. So it's a binary or whatever thing that corresponds to each one. Then the question is, we'll make the derivative as 0 and trying to find the w that makes this equation happen. Then to solve it, what is the computation complexity? Or are you familiar with the definition of computation complexity?
Yeah.
Okay, yeah. Then the number of basic operations you have to do to solve this equation.
So like you will take like the inverse on both sides, and then I don't know how to calculate the complexity for that.
Any volunteers on calculating this computation complexity?
It is just the complexity of whatever the multiplication is going to be,
Yeah.
like the matrix multiplication.
Correct.
Yes.
Then can you give us some like details about how you can deal with these operations? Of course, the hint is you have to use the number of d and n because they are the dimension of this data.
Yeah, but that's transposed, so like the dimension of the matrix for x is like n by d, right?
Yes. So I can give you hints. So to solve any d by d dimension system, so the complexity is d to the power of 3. Okay, this is the hint.
Oh, okay.
Then, of course, the answer is not limited to the d to the power of 3. Okay, then the second case hint is that, so on the left-hand side is matrix multiplication. Yes or right? Yes or no?
Yeah.
Okay. The right-hand side is a matrix vector. Because x transpose y, so it's n by d multiply d by 1, so gives you n by 1, right? So here we can decompose the problem into 2 steps. The first one is count the number of operations on the right-hand side and on the left-hand side. So on the right-hand side is big O notation of nd, because this is the dimension of n, so when you're trying to multiply the matrix x with the vector y. The second one will be, we'll calculate the matrix multiplication is n multiplied d squared. And then you're trying to solve the system, of course, linear system. And then here, typically, when you're trying to solve the d by d system, the complexity is, for any d by d system, it should be like big O notation d to the power of 3. Then the question is, overall, what is the computation capacity by consider all of this?
NDQ?
Sorry?
NDQ? Like N and D and then Q?
Oh, what is Q?
Like
the
Q,
NDQ.
Q, like.
Why?
It just like took the common between all 3 of them.
It doesn't mean, I didn't see it's a common between the 3. It seems like you're multiplying this,
Yeah.
or
Kind of.
you're trying to select the highest order of
Yeah.
this multiply of d and
Yeah.
d. But typically, you're doing this step by step. So it is summation of the 3.
Okay.
Summation of d and d squared and d to the power 3. And of course, this is dominated by nd, so this can be ignored in a big O notation because this can never grow faster than nd squared. So basically, the final answer is in a big O notation of nd squared and d to the power 3. And the problem is, this will give you a closed form solution for the least square problem, right? You can see that when you take the inverse to both of sides, so the optimal W that gives you 0 derivative is the inverse of x transpose x multiply x transpose y. And the problem is, when D is very large, how is it possible to fit into this closed form solution, right? When D equals 10, you can do it by hand. But when D equals to billion, what kind of computation capacity you need to solve it, for example, in 10 minutes? Because there is no way. So people are thinking, alternative way, when the dimension of the data is very large, right? So here, for example, an example of a very large D is, for each of the entry, this can represent an article. So each D will be the total number of word in an article. So that's why we're going to use gradient descent, which is the way that we use a gradient. So we find the gradient somehow indicate certain characteristic of the loss function. The routine of gradient descent is that we start from a random guess. We don't know the optimal solution, but we can, based on our experience, we can start from something that we feel is close to the optimal. We denote at W0. But a comment on this one is typically we don't necessarily to denote W0 or W1, W2. The reason is that it is in terms of mathematical notation, you're mixing with W to the power 2, W squared. So typically when we're going to denote the initial steps, the index of time, and we have to add a bracket. But for lecture purpose, I don't want to, get confused with all kind of bracket. So here, every time I will make it very clear, this 0 is the index of time step, or the steps, rather than, the power. And then we will try to use this gradient function to find a direction that help us make the loss function lower than the random guess. And then we'll start from the first step. We'll calculate gradient based on the first point, W1, and then trying to find W2 that may make our current loss function even lower. So we'll keep repeating these steps. So the question is, when should we stop?
Then you cannot generate a better guess.
What kind of percentage?
Percentage.
No.
But the improvement is getting slow.
Yes. And also there's another way to stop it.
You reach conversions.
Until convergence, yeah, quite close to his idea about doesn't improve that many.
Mm-hmm.
And another simple way to do that, what are another way to stop it?
Define number of steps.
Definitely, yeah. Of course, the first step is you can stop by defining, say that I want to run for 100 iterations and then stop. The second case is you can find whether it get converged or whether you do not make enough improvement by keep doing gradient descent. But there are a lot of ways to quantify the convergence. For example, here the example is so when the derivative, the gradient goes to 0, because you're using the gradient to update your decision. When the gradient is 0, so we have no way to further improve it. But in most of the cases, the gradient will become smaller and smaller and smaller and never goes to 0. So you can enforce the maximum number of iterations to stop it. Or you can have some approximation of this one. For example, when the absolute value of cost function close to 0 or smaller than some prescribed given number of precision, or the second order of derivative of the cost function is smaller than certain given one. So, and also you can have a hybrid and a combination of different kind of stopping criteria that trying to give you more robust performance. In a lot of cases, that this the one WT you got when the derivative equals 0 will give you the global optimum. In that case, in most of the cases, it is under the umbrella of convex optimization. So saying that if a function is convex, so when the derivative equals 0, this indicates that you are finding the global optimum. So for example, the square function, you can have the x-axis will be the value of the model, and this is the shape of the curve. This is just a one-dimensional example. And here, the one gives you the minimum value will be the global minimum. And later, I think we will wrap up gradient descent first, and then if we have time, we will cover the basic idea about convex optimization and some properties of convex optimization. And here, let's virtually go through all this gradient descent. As I said, the x-axis will be W, which is the model parameter you're going to learn, and this is just a one-dimensional example. So it's just a scalar. For example, W0 can equal 1 or 2 or just a simple number. We start from this value, and we input this value into our loss function, so we can calculate the value of this cost function. And then we want to take the derivative at this point. Definitely, because this is a very simple example, we can virtually find the minimum, which is in this area. But without doing this, we have to find a way to make W0 approach to this minimizer, but we don't want to go further because in this case, the function will go up again. So here, at the first step, we start from a random guess W0. So that's why, based on experience, we don't want to make this one too far away to this point. So this will require some experience on your data. And here, once given the W0, we will calculate the gradient at this point. So we will draw a tangent line on this curve. And definitely over this one, this is the direction, tells us if you go with this direction, the value of the cost function will be lower than the random guess. But the problem is, how far do we have to go, right? If we take this step, then we are getting close to the minimizer, right? But if we take a very large step, we go over this minimizer, and actually it requires back and forth to find this minimizer. But anyway, the first step is to find the line with the scope of derivative. And typically, this derivative is negative to show that going this way decrease your cost function. And then we have to take a step towards this one. For example, this step, if it's small enough, so we will always have a loss function smaller than the first step. So we want to decrease it and making this is in this example increase W0 so as to decrease the value of the cost function. And then we are moving to W1 by taking a prescribed step size, this one. Then we'll keep repeating this process, saying that we start from W1 and draw the tangent line over the curve, take a step again, and then find W2. So this is a line with the slope again. Again, this slope is still negative, so saying that you keep going to this direction from W1 to the right-hand side, your cost function have the possibility to going down. If you go in another direction, definitely this value will go up. And then we will keep repeating this one from W1 to W2 to W3 to W4 and to something that you're trying to stop it. As in some of the case that, for example, at your fourth step, you will go over this minimizer. Then again, you always need to check the derivative at this point. So if you draw the tangent line at W4, at this time you find that the direction of this derivative or the tangent line changed, saying that this is the indicator to say that you go too far, you miss the minimizer. Then the slope is positive to say that if you further go to the right-hand side, your cost function will go up. But if you go back, but with some carefully designed step sets, you have the potential to find the minimizer. So in this case, you're moving and you follow the direction of the newly calculated derivative and then go back again to find W5. Until you find that W5 has exactly zero derivative, so this means that you finally find your minimizer. If we try to write it mathematically, is we start from an initial guess, W0, and then we use a gradient, is nabla f over W0, in the direction with the step size alpha 0. So the reason that I add a times index to the step size alpha is you have the freedom to make it fixed or make it diverse, and in most of cases you have to make it continually decreasing, especially saying that when you are far away from the optimal, so you take a large step to save your computation. But when you're getting closer to the optimum, you have smaller step. You want to have a high precision that you are as close to the optimizer as possible. Then you keep repeating this. So an easier way is you just replace step size 0, 1 with t and t plus 1. And this is for the number, and here t is the number of iterations you are running your gradients and algorithms. So exactly, if you want to stop, so either you have never get a chance to make further improvement, or you can see that the gradient that you're calculating is is very small and have no improvement. So in most of the cases, we'll say that the right-hand side approximates the local minimum. So the larger this value is, the longer distance you are from the optimal solution. So the smaller this value is, the closer you are to the optimal solution. So when this is smaller than a prescribed small enough scalar, you can stop running your gradient set. And as we discussed before, the right-hand side can be substituted by whatever quantities that have correlated with the optimal solution. It can be replaced by the Hessian matrix. It can be replaced by the objective function itself. Any questions so far? Then there's a confusion between different kind of space, like data space and parameter space. So what are the difference between these two spaces?
parameters could be the parameter space would have all the possible parameters you can have in this problem.
Yeah. So the name directly told us. So data place is the domain of the data, means the training data, training label X and Y. It can be exactly the same. So on the left hand side, so the X and Y will be the data. So for example, the x-axis will be a simple x, for example, your age, and the y-axis will be, for example, when you're a baby. So the y-axis should be the height. So there's a correlation between how many months you have and the height you are. So typically there have some positive correlation. And the parameter space typically refers to the space of the model parameters. So on the right hand side, the x-axis and y-axis corresponds to W. For example, this is a two-dimensional example. So x-axis will be W1 and y-axis will be W2. So in this case, so the x-axis corresponds to this one. So typically, when W is a vector, if you're written by hand, so we add a bar under this W. So equals, for example, W. So times them 1, dimension 1, W2 times them. So these two are the axes of X and Y. And we are trying to, and these are the contours, so it's very similar to the mountain side. You're trying to, this is a optimal solution. You can see that on the figure for different over the range there are values of the loss function, and so from 5,000 or to 2,500, and this is the optimal solution. So we're trying to find, no matter when we start with this W0, we're trying to find a path that's closer to W star, right? So don't be confused about this two definition because they are referring to different things.
I'm sorry, by parameter space you're referring to like feature space or like
So again, you are confusing with data. So feature means the feature of data, the feature of training data. So it's related to the data space. So in this example, the feature dimension of this one, what is the feature dimension? Typically it's 1, right? Because the x-axis is x, y-axis is y. So in such one dimension, you are trying to learn a line that mimic the data distribution. For example, this is just a linear regression.
Yeah, that I understand. I have a problem with the parameter space. I didn't
Yeah.
understand.
So here in most of the cases, this W can be related to dimension of data, but not necessary, because in a very simple case where the label is just a dimension, it's just a scalar binary. So here the dimension, C, but here, so for each example, Y is in R. But in most of cases, this the label of a sample can be denoted by entire dimension. In that case, W should be also correspond to any dimension in your interest. So for example, in your neural networks, you have different kind of layers. Then one W is a matrix about how many layers you have, and in each layer, how many of neurons you will have. So this is dimension of W. So this is totally defined by yourself. This is the dimension of the model you're learning. So somehow in some of the cases, it's related to the dimensional features in the training data, but not necessary. Then we have illustrated the behavior of graded descent in one dimension example. And here, let's use the right hand side to show that in 2 dimensions, where the model parameter W is W1, W2, how we can do that. So an example of this one will be linear regression, right? Linear regression, we're trying to learn a hypothesis, a hyperplane. Very easy, like y equals ax plus b. Then here, the W we mentioned is a and b. So it's a 2-dimensional example. So we'll start from random guess, this blue star. Hopefully it's closer to this one. We don't start from the very far corner. In that case, it means that we will take longer time to get close to the optimal solution. With this random guess, W0, you insert back to your function. So here, okay, so this is the one we're trying to learn. And W0 means A0 and B0. And we insert back 2, so it will give us a random line in this figure. And of course, if you take a look at the figure, we want to find a line that is close to the data distribution as possible. So then we calculate the gradient at this point. And you see that I'm trying to use another one. Make it very clear. In 2 dimensions, so we have a lot of contour. And obviously, the optimal solution should be in this area. And somehow we'll start from anywhere that give us, for example, 5,000 value. We draw a tangent line here, find the negative, so this is the derivative, and we'll find the negative direction, derivatives that help us reduce or decrease the value of the cost function. So we will go in this way. And also, depending on your step size, if you're choosing a small step size, so you just stop here. So this is W0. In this case, A0, B0. And then you take step size here. We'll start with A1, B1. So when you're trying to input it back, so Y equals A1, X plus B1. So this will give you an updated value. So here you can see that your line is changing from a random one to a line that's closer to the one you're trying to learn. And you'll keep doing this. And from this point, so this is another contour. You draw the tangent line, calculate the gradient, find because this is a very easy part I'm drawing, so in the same direction. But there's a way that you're using different direction. For example, if your contour is like this one. So they may not necessarily have the same line, but in the same way, say that for example, we're calculating the contour over there, we'll calculate the derivative, find the negative direction, go with the step size, and here we'll update our value over here. So it's closer to the optimal solution. And you can see that our guess, the blue one is getting closer to the red one, which is the ground truth minimizer. And as I said, so this is an example to saying that in a lot of cases, when the step size are not choosing properly, so you will go over, you're not in the shortest direction. For example, the shortest direction is you just draw a line from the initial point to the optimizer. But because you don't know the location of this optimizer, and you're trying to trail different selections of step size, so you will have fluctuation that when you go far away, then you will the gradient will draw you back. So until you are reaching, you're getting closer to the optimizer. Any questions so far? So we have gradient descent in both 1 dimension and 2 dimension. And here, if we get back to the least square example, we will have in the first line, on the left-hand side will be the definition of the objective function, and the right-hand side will be the function for its derivative. So any question in terms of how we can calculate the derivative in the form of matrix multiplication? Okay. So this will also be included in the homework to derive the derivative of least squares. Definitely you cannot think that you directly give the answer, you have to take steps to do that. And then you just through the formulation of gradient back to the gradient update rule. So originally this is a gradient of xwt, and then you substitute between this one. So x transpose xw minus 1. So here, this is the derivative of loss function. And another, yes please?
Can you go back? What exactly is WT here?
Which one?
Like in the last line, WT, what exactly is WT? Like, what do you mean by that notation?
So this is your
Yeah.
predicted label.
Okay, just one
Y
label.
is your branch label of your training data. So this is the difference between these two. And how you get it, because you take derivative of the function, because this is the cost function you define. You take the power of the absolute value of the difference between your predicted value and the true value. So in this example, in the linear regression, ax plus b, so you can write, if you say w is defined as a vector of a and b, so it is x transpose wx.
Yeah.
Right. So this one. There, meanwhile, you these two. But be careful when you're trying to, I just randomly write, you have to check the dimension of the matrix and vector and make it happen.
But is it just like one label? Is just one entry, or is it for all the data? Like, is the x right now all of the data?
This depends on how you define your training data.
Yeah, okay.
So typically, the a very overall idea is, so this x is the whole training set, the capital X. I draw over here. Is n by d. N is the total number of training data you have. D is the dimension of each data entry. Also, you can also limit. If you don't want to use all of your training data, you can say this. You can define.
Yeah, my main question here was basically because that in the definition of the gradient you mentioned above, you are computing this gradient which seems large, and now in the gradient descent you are computing that again and again.
Yes, because t is the time step. W is changing, so
Okay.
the gradient is changing.
Okay.
With different W, so your magnitude of the derivative are changing, right? Yeah. So the W that give you the smaller derivative means that you are getting closer to the optimal solution. So okay, another question about computation complexity. So previously, I will show you how to, for least square problem, how you derive the closed form solution, and we know that the computation complexity to calculate the closed form solution without learning, just to try to find the optimal solution with one step, with all of your contribution capacity, is in big notation of d nd squared plus d to the power of 3. Then, what is the computation complexity of gradient descent? Let's take it easy. So for each iteration, what is the computation complexity? How many number of operations you have to do to deal with the gradient descent step in each iteration? Any ideas on this one? Go ahead, go back. So this is the thing you have to do for each iteration. You have to have a subtraction. Typically, if we assume D is, W is in dimension of D, so it's a subtraction between D dimension minus D dimension. And the second part will be a multiplication between the step size, could be a scalar, and something that the dimension you have to calculate yourself. So the main idea is, imagine that typically the calculation requirement about gradient descent could be larger than D. Then what is the computation complexity to calculate the gradient itself?
Isn't it the same thing again?
Why? Why is the same thing? So an intuition is that it must be, it should be in some cases, it should be, it should have less step than the closed form solution. Otherwise, why do we bother with training? We just calculate it.
That's what I was asking.
Yeah. So there's a hope that it should be smaller, right? So definitely the answer of this question could be different from the closed form one, right?
Is it because you can pre-compute the xt, like the x transpose and x before, and that remains the same? and then you just do the multiply with W and then by.
In most of cases that we don't have to solve the d by d system, the d by d equation again. So here, again, we can decompose it, right? So x, the matrix x multiplied w is in the dimension of nd, and the subscription is additional big O of n. So these two steps is summation of these two is big O notation nd plus n, because nd is dominant, so it's also big O notation of nd. And then we have to further calculate the capital X outside of the bracket. So for this step, it also requires additional big O notation of nd. So if we sum all of this up, so what is the complexity of gradient descent?
Just ND.
Yeah, so just nd. So here, this is the cost of gradient descent iteration is in big O notation of nd, because in this case we don't have to calculate x transpose x, so which dominate in the closed form solution. We'll have to solve the d by d system, which is big O notation of d to the square d cubed. And does it mean that gradient descent is always better than closed form solution? So here, in each iteration, the complexity to calculate one gradient is in big O notation of nd. So I don't bother asking a question. So in total, the total complexity of running gradient descent is you just multiply the total number of iterations. So you'll have the complexity of gradient descent is in big O notation of ndt. So how did you know that one gradient descent is better than the closed form solution? So in this case, we also call it like normal equations. Normal equations is the closed form solution of least squares. So in which case that we prefer to use gradient descent rather than calculate by hand?
Where the computation by hand takes more time?
Sorry?
Where the computation by hand takes more time?
Yeah, so then how you can quantify you're getting more time? Okay, I will save this to the next lecture. So we'll discuss again. So think about how you can do it. And so for tonight, the lecture I will submit, I will stop here. So give you a chance to think about in which cases you prefer closed form solutions, in which cases we can use gradient descent to give you better performance and or save your computation capacity. I will stop early because last time I only used 6-7 minutes, so I will stop 3 minutes and I will save another 7 minutes next lecture. I don't want to waste any of your time. So hopefully see every one of you in the next lecture. I know that the first half of the lecture is a bit boring because it covers a lot of mathematical function, but as you progress, you will enjoy the in-depth discussion in terms of the theoretical machine learning. Okay, so feel free